So I am going to share the questions and answers. But I'm actually on top of things today. And in a few seconds,
Nick,
you should be seeing this. There we
hey
go.
Nick, I got my ARRL magazine, a day or two ago. Just after we went over, I started reading it just after we went over the last class, and most of the stuff in it, most of the articles and everything were on antennas this time. So it actually made some sense.
Well, you're actually going to learn a lot, and you'll actually be able to use everything I'm trying to teach you.
Yeah.
All
Well,
right.
when I was reading through their stuff, it made sense because we just had it in class, so that was kind of neat.
I haven't read this month's QST. I'll have to look at that. T3C07 is where we're going to begin tonight. It asks, what band is best suited for communications via meteor scatter? And this is just information I have to give you. 6 meters works out perfect. It works out very well for that's 50 megahertz band. It has to do with the fact of the length of the wave and the distance that the ionization will occur from the trail of a meteor. And basically, that's the parts breaking off the back or the end or all around the meteor as it comes in the sky. It burns up and creates an ionization path. You can bounce off that because it's up there about 15, 12. I'm sorry, it's up there about, I don't know, just below right at the bottom of the troposphere. So when it does that, you get really nice bounce and nice skips. You make contacts easily 1,200, 1,500 miles away. So we'll move on. So keep in mind, if you ever want to bounce a signal off a meteor and it gives you a scatter, so it'll be slightly distorted, but it's still intelligible and you can make contacts and work people. Uh, a good 1,000, I would say, to maybe sometimes if you're lucky, as much as 2,000 miles, but 1,500 is probably close to the max. And it's pretty cool. Okay, what causes tropospheric ducting? Tropospheric ducting, I don't know if I covered this in your class, but I think I did. It occurs because a temperature front comes in and a warm set of air or a cold set of air gets trapped between layers of the other. So a warm set of air gets trapped between two cold layers, or a cold layer gets trapped between two warm layers, and they act like ductwork. Well, as long or as far as that duct is created, signals will bounce off of them, usually 2 meters, 440. They'll skip incredible distances. I used to work a repeater every morning down in Florida from here in Michigan because at one time of the year, a few years ago, there seemed to be a ducting going on every morning. And actually, we check in the repeater, say hi to everybody, and they got to know me down there in Florida because we had an opening for about the same time every morning, right when I was going home from work. And I checked for it every morning, and every morning on my way home for work for about a month. I think it was in the spring. I was able to get through. It might have been in fall. I don't remember. I'm getting old in age. So the answer is D. Temperature inversions in the atmosphere create the conditions for ducting. That is really cool because ducting does a really nice job in there's no distortion in ducting. It skips in the duct. It can be a long, 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 long ways. What is generally the best time for long distance 10 meter band propagation via the F region? And from dawn to just before sunset, A is the answer. And I'll tell you anytime in the daytime, but uh, dawn to just after sunset is when 10 meters open is open in the daytime, it's open. Right now, it's been open. Tom was just playing a little bit of it on his rig, and I heard it from here. And I'm sure that, well, it's probably here no longer because it's past sunset here, maybe a little too long. I'm not sure. It's getting earlier nowadays, the sunset. Which of the following bands may provide long distance communications via the ionosphere F region during the peak of the sunspot cycle? The answer here to this question is, well, during the peak of the sunspot cycle, and we're approaching it now, I think. We won't know if we're at the peak till after it's over with. Uh, there's really very little effect of the F region on anything above 6 meters. The F region will affect and reflect back to Earth 10 meters. I did show you a drawing of the tropospheric layers, and those layers aren't that they're different layers of the air; they're that where the ionization is. And ionization is charged particles from the sun filling up the troposphere, or I'm sorry, ionosphere. So, um, 6 meters and 10 meter, particularly 6 meters, which we oftentimes refer to as a magic band. Boy, 6 meters will surprise you. Sometimes 6 meters is only local. There's nothing you can do with it, and all of a sudden, bam! It not only skips, but it skips multiple hops to incredible distances. Then it goes back to being stubborn like 2 days, or well, the next day, or of course, at sunset, you're going to lose it anyways, right after sunset. Why is radio? Why is the radio horizon for VHF and UHF distance more distance or signals more distant than the visual horizon? Well, the answer to this is the Earth has a magnetic field. The magnetic field of the Earth tends to pull or bend all electromagnetic waves. All electromagnetic waves can be bent with magnets. It's how the picture screen on old TV worked. The image was deflected by magnetic fields to move it along the screen. And that's what, as it scanned across the screen, that's what made the picture. So when you transmit uh, uh, I'm looking for the word I've lost. Anyways, when you transmit from point A to point B on directly, what we often as hams like to refer to as line of sight, it's really not line of sight. It's actually line of sight plus the bending. The bending brings the signal a little bit past the curvature of the Earth, bends it down a little bit past. So a signal will often carry just naturally a little past the visual horizon. Okay. Now, when I was young, they used to refer to it as ground wave, a portion of the wave that hugs around the curvature of the Earth a bit. I don't know if they still do or don't. I haven't heard it referenced that as years. But boy, it sure is a good way of thinking it. For a little bit, as long as it can, the signal hugs as close to the Earth as it can because of the magnetic field of the Earth. Fortunately, it doesn't push it away because that might screw things up for us. T4 AO1, which of the following is an appropriate power supply rating for a typical 50-watt output uh, FM transceiver? Let's think about this one before I answer it. I know it shows you the answer there, but, and by the way, I think the answer technically is not shown. Anyway, if you got a 50-watt transmitter and you want to know how big of a power supply you need for it to run it in the house, let's begin with the radio transmitters mobile, so it's designed to run on 13.8 volts. Okay, you got 50 watts. So if we take 50 and we divide, well, let me explain why. If we've got 50 watts, the power formula is P equals IE. Remember, I told you to draw the circle with the P on the top, the I on the bottom, and the E next to it. Cover up the one you're looking for, and that's the formula you need. In this case, it'd be P over E. So if we took 50 and divided it by 24, we'd come up with about 2 amps. But there's a flaw in that. And remember this flaw. Transmitters are rated in power out, not the power they consume going in. Almost all amateur radio transmitters and amplifiers use a Class C amplifier, and a Class C amplifier, I believe it's Class C. Boy, I hope I'm right. I'll correct it if I'm wrong. It doesn't matter. All amateur amplifiers and the finals to your radios are amplifiers. They're only about 50% efficient. So if they can output 50 watts, they need 50 watts more coming in. So our calculation was for 50 watts, and we need 2 amperes. But in fact, you're going to need 4 amperes. By the way, D says the correct rating of supply must match the sum of the maximum current used by everything hooked to the supply. That's true. So if you're buying a 50, what it's trying to tell you there is, if you're buying a power supply for your station, you know you got a 50-watt mobile, you don't want to buy a 4 ampere or 4 amp power supply. It will power just the mobile, but you're probably going to have other little things you're going to attach to it too. I know my power supplies have all sorts of 12-volt devices hooked to them, meters and things like that with lights. That all draws power. So you want the 4 amps plus whatever else you might need. So maybe I want a 5, 10, or 15 amp power supply. Tell you now, there's no power supply in my station less than 20, and most of the main power supply at my main station is 50. So I have plenty to work with. This is a case where bigger is better for you if you can afford it. Which of the following should be considered when selecting an accessory SWR meter? Well, answer A, there's the frequency and power level at which the measurements will be made. SWR meters usually have a frequency range of which they can operate. And they also have a maximum power range of which they can operate. So you want to use one that's rated for enough power and for the right frequency for your rig. A CB SWR bridge is designed for 4 watts. If you put your 50-watt mobile 2-meter radio and transmit through it, you will fry that little puppy. Not only that, it's designed for 11 meters, which means its measurements forward reverse at 2 meters would be useless. You want a meter for the band you're on and for the frequencies you're going to be operating at and for the power level. So answer A is correct here. What are short, heavy gauge wires used for a transmitter's DC power connection? All right. I covered this for the general class just the other day. A couple things to remember. One is voltage drop, and that's covered here. The answer A is to minimize voltage drop when transmitting. Every piece of wire has resistance. You're only operating a transceiver or a radio off of 12 or 13.8 volts maximum, usually. It's not much voltage. Now, in a household wiring, we're running at 110 volts. At 110 volts, if you have a voltage drop of 1 volt, it's not going to make a significant difference. But at 13.8 volts, 1 volt drop is almost 10%. And that might make a significant difference. So when utilizing wire to feed your radio, you want to use the voltage drop formula, V equals IR. It's the it should be E equals IR to be consistent. But the voltage is equal to the current times the resistance for everything, for every electrical circuit. And wire is a resistor. It might be a very, very low value resistor, but it can have an effect on small voltages. For this reason, devices that run on, say, 5 volts or 3.3 volts, like within computers and things like that, they can't run those off of very long distances. We're talking only a few inches before they get in trouble. If you're wiring your radio in your car, it's a 50-watt mobile radio. And you say, okay, at 50 watts, I'm going to need 4 amps from that previous equation we just did. And you're going to say, okay, well, 4 amps, that's not much. I should probably be able to get away with, probably, let's see, well, if I look at a household wiring chart, number 14 can support 15 amps, and number 16 wire can support I'm sorry, yeah, 15 amps for number 14. Where was I? 16 wire. Well, that can support 10 amps. And number 18 wire, that can support 8 amps, and so on. And boy, that'd be great. Except you don't have to worry about the voltage drop there. So I would tell you that you probably don't want to feed it with less than number 12 wire, which according to a household wiring chart is good for 20 amps. Well, that would be great if there weren't no voltage drop. And if you're only wiring a couple of inches, it probably would be great too, even at 12 or 13.8 volts. But you're going to find that when you route a wire around the car, you can't make a direct path. And believe it or not, it's not unusual to have to run the wire around from the battery around the uh, uh, under the hood, by the firewall, in through some hole into the area of the instrument panel, and run it across to wherever you put the radio. That can end up being 10 or 15, 20 feet of wire. So keep that in mind. As a practical matter, you want to keep that wire as big as you can if you can afford to get away with, and is practical. I mean, you're not going to run wire that's 2 inches in diameter, although you wouldn't get any voltage drop from it. Greater the diameter of the wire, the less the voltage drop, because it offers more surface area for the electrons to flow through. How are transceiver audio inputs and outputs connected to it in a station configured to operate using FT8? FT8 uses the audio inputs and outputs of a radio through a conversion unit that hooks to a computer via or a keyboard via a computer. So you hook the input and outputs to that conversion unit, the FT8 adapter, if you will. You plug the FT8 adapter in the computer, and the computer keyboard then will be able to be used to control FT8. Correct answer is C. To is you want to connect um, you want to connect the conversion unit or adapter uh, to the audio cables. There'll be an audio in, audio out, or mic in, headphone out type connection. The the interface or conversion unit, as they refer to it, and I was looking for this drawing. I knew it's here. There we go. The interface gets connected to the input and the output audio. Now, some are designed to do like this one, where you connect one to the computer and the other to the, and some are designed to go everything through the interface. So to connect FT8, yeah, you read the manual with it, it'll tell you it's pretty simple to follow, but you do need audio out and microphone in for the FT8 signal to be able to operate. And you connect your adapter to this. By the way, this shows a setup which really isn't common, but it does exist. There are all sorts of TNCs and MPCs, terminal node controllers, which is predominantly was originally used for packet, and multi-protocol controllers, which is designed so that you can get all sorts of digital modes from the same box. They're all cool. They all cost more money the more fancy they are, but they all work great. You can buy inexpensive uh, uh, interfaces for FT8, um, for packet, etc., or you can buy really complex and cool ones. They just it's a budget matter. The more modes you want to operate, how you want to set up things, that's things you'll decide as you go along. Where should an RF power meter be installed? Okay, power meter and SWR meter pretty much go in the same place. They go in the feed line between the transmitter and the antenna. The goal there is to measure what's going out to the antenna, that's a forward power, and to measure what's being reflected back from the antenna, that's the reflected power. The ratio between the two is the standing wave ratio, and that is what an SWR meter indicates. But it is actually a special type of power meter. The most accurate measurements are made with precision power meters, but you don't need it. You need relative for most operations. But for repairs and laboratory grade stuff, they use very precision power meters. And they use two of them, one measuring the forward power, one measuring reverse, and sometimes they use even three in the lab. That's not necessary for most ham station. Those meters run about, I don't know, what's a bird watt meter today, Thomas? Is it under $5,000? And three of them would be quite an investment. And then you need what they call precision slugs for them. They're several $100s a piece for each one. They come for each band that you're going to use them in, and they're a fortune. Those of us who do RF repairs from time to time, we own such things in our labs, but we don't keep them in our stations. It's not necessary. You can buy good SWR power meters for your station for a world of a lot cheaper. During the break, I'll grab one and bring one up from my station in the basement. One that's 2 meters and one 2 meters, 220 megahertz and 440. What signals are used in a computer radio interface for digital modes of operations? Well, you need, in order to hook up, and it was covered in the previous thing a bit, previous question, 2 questions back. You need to hook up any sort of computer interface for digital so that it's connected to receive audio, transmit audio, and transmitter keying, transmitter on and off. If you think about it, it makes a lot of sense. It's got to receive stuff and put it on the screen for you to see. When it's time for it to send what you're typing, it's got to turn on the transmitter and then send audio out, which is going to be interpreted by the computer at the receiver on the other end and translated there for the person there to see. Which of the following conductors is preferred for bonding RF? Well, I'm going to take exception with this, but this is the answer that the FCC expects you to answer. The FCC still believes that flat copper strap is the best bonding material. The National Electric Code doesn't necessarily agree with this. In fact, the National Electric Code is a little different, but a flat copper strap is a good bond no matter what. The other answers, a copper braid removed from a coaxial cable. Well, if it's a big enough coaxial cable, it might be decent, but it won't be as good as a flat copper strap, which is more dense, is specifically designed for bonding. Twisted pair, by the way, is telephone wire. That won't work. And steel wire is never as efficient as copper. So the best answer here is a flat copper strap. How can you determine the length of time that equipment can be powered from a battery? Well, it's a pretty interesting question. Well, batteries have amp hour ratings. How many amps? Amp hour ratings is how many amps it can produce for an hour. If you draw that number, let's use easy number. Let's say it's 100 amp hour battery. You can draw 100 amps for an hour out of it. Not all batteries can maximum draw, but in theory, you could draw that. And you could operate drawing 100 amp load for an hour. But generally speaking, you're not going to do that, and batteries won't withstand that. That'll damage the battery. So remember that as a practical answer. This is the answer from the book, which is theoretical. You take the amp hour rating of the battery and divide it by the amount of current you're going to draw out of it. So if you're hooking a 100-watt light bulb running, I'm going to make this easy, at 100 volts. I'm sorry. Yeah. No, let's go 10-volt battery, 100-watt light bulb. If you're using a 100-watt light bulb, 100 watts divided by 10, it's going to draw 10 amps. And if you got a 100 amp hour battery, you're drawing 10 amps out of it. It's going to provide almost, but not quite, 10 hours of operation for that light. The answer B here, divide the battery ampere hour rating by the average current draw of the equipment, is correct. If the current draw were constant, not going to change, you would draw, the average would be whatever the maximum current draw is. Now, if you're operating a transmitter, you're not going to draw continuous power. So if your radio's drawing 4 amps, like in the previous equation, then a 100 amp hour battery, which by the way would be a world of a big battery. Most batteries are not 100 amp hour batteries, not even car batteries. In true current, they're about I don't know. I think they're about a quarter of that, maybe 25 amp hours. But if you had 100 amp hour batteries, that'd be a new high amperage lithium ion battery. You're drawing, you got a 4 amp transmitter. That's 4 amps on transmit. You don't transmit 100% of the time unless you're leaving it in digital mode at maximum power or something like that. You do some listening, right? So you can figure what percentage of listening and what percentage of transmitting. Let's go 50-50. Listening time, it only draws a few milliamps, so you pretty much say that's close to nothing. So if you want to guesstimate, because calculating it precise requires metering it all the time and doing the math as it goes. If you want to guesstimate, you say, okay, I got a 4 amp hour transmitter or a 4 amp transmitter because it's a 50-watt transmitter and it's 50% not efficient. I'm going to divide my 100 by 4. That's 25. But I'm only going to be transmitting half the time. I'm going to be listening the other half. So I can double that. So it'll probably run for 50 hours as a station. Does it ever work out to give you that? Not a chance. Because most batteries, no matter what their rating are, they can't be drawn all the way down to their maximum. A lead acid battery can only go down about 20 to 30% before you damage the battery. So you don't get anywhere near that out of a lead acid battery. Some lithium batteries will go down about 90%, and you can draw 90% of their charge safely, but you'll never get 100%. So as I said, this is a theoretical answer and gives you a rough idea. Doesn't give you precise. What function is performed with a transmitter and digital mode hotspot? Well, digital mode hotspots. Well, I'm missing the antenna for the second channel for this one. But this, if I don't know if you see it or not, because I can't see it, is a digital mode hotspot. When you're operating in digital mode hotspots like that one will allow me to hook that to my local repeater digitally through the internet. And then I can talk to that from my handheld. And even though my handheld might not have enough power to get to my repeater, it will allow me to communicate through that repeater just as if it could. I'll actually be entering the repeater's system through the internet digitally, and I will be receiving the signal back from my hotspot, not from the repeater directly. But it works really good. So if you want to set up a hotspot in yourself in your station, somewhere in your house, I found this hotspot works about all the way to about a half mile away. So I can take my handheld radio, I can put it on the lowest power setting it has, my two-way, and I can work a repeater with no problem that's linked to it. Of course, it has to be a digital repeater, and it has to be hooked up for the same protocol, the same mode of digital as the repeater. Many little hotspots like the one I just showed you actually can be configured for different digital protocols. Where should the negative power return of a mobile transceiver be connected? And the ground of the body of a vehicle is the entire chassis of the vehicle. But do not ground or run your power connection to the chassis of the vehicle. Two things will occur. Any noise, RF noise made by the vehicle will be carried down that path. So you'll pick up noise. Two, as good as the guys who work on the line are that build those cars, not every one of them had a perfect day where every single bolt, every single weld, every single connection was perfect. So the body is not a reliable return path for the electrical for a radio, especially one carrying enough power for like a 50 or 30 or 50-watt transmitter. The answer A is the best connection point. The the 12-volt battery chassis ground, the point where the battery itself is grounded to the chassis, which is essentially the negative terminal of the battery. I like to run my power connections all the way back, plus and minus, to a I added on in my I always do in my vehicles. I add on a little box that will hold a number of extra fuses. I put my own fuses for the radios in the under the hood, and then that is connected to positive terminal of the battery, and the ground wire I bring back to the radio is hooked right to the point where the negative terminal of the battery is grounded, where the wire goes to ground to the chassis of the vehicle. Closer you are to that negative side of the battery, the better. So, like it says, the 12-volt battery chassis ground. And that's the point where the battery itself is grounded. What is an electronic keyer? Okay. Electronic keyer is a device that assists in manual sending of Morse code. 12-volt keyer is a device that when you hook a set of paddles to it and you push one side, it sends dots. You push the other, it sends dashes, dots. You don't have to type the dot and dash. You only have to move your fingers back and forth, and you get the dots and dashes out of the keyer. It's a pretty simple device. Some modern radios have them built in. What is this is operating uh, frequency and tuning controls, etc. We're going to go through the controls of your radio. T4B01. What is the effect of excess mic gain on a single sideband just transmission? If you turn the gain up on a single sideband on AM, doesn't matter. If you get up to at some point in time, some level, even FM, it doesn't improve things. Amplifying the audio is not a good idea in radio. It's become a popular thing in CB, but it creates distortion. That distortion not only distorts the audio, but can end up causing spurs and splatter. Spurious signals are signals you don't want. They weren't intended. Splatter is bandwidth that's too wide. Okay. So modulation, it says down below, over modulation of an AM or single sideband signal, basically speaking too loud or setting a microphone gain too high. Well, it will result in distortion of the transmitted signal. What time is it? It's time enough. I'm going to stop this share. I'm going to go to the funny drawing screens that I usually use, and I'm going to share them for just a second. Share one screen. I don't know which drawing screen I can grab. Let's take this one. This isn't necessarily a drawing for you. It's actually for the other class. So it didn't, I don't see it. Stop the share. Let me try again. Share screen. Here we go. Okay, do you guys see a couple of parallel circuits? I want to make sure I got the right screen. Maybe not. Let me try this again. I just need a blank screen and it's giving me let's try this again. Share screen. There it is. Here we go. You should see this now. Okay, so I'm going to clear this out. Where is the darn thing? Here we go. Make this nice and wide. Just going to wipe this all out. All right. When you overmodulate, every transmitter, every transistor in every circuit has a maximum uh it has a maximum or peak voltage and current that it can withstand. In this case, it's the voltage we're going to pay attention to. So, if you can imagine that if we looked at the parameters of a transistor, the manufacturer would tell us that if this is 0 volts on this line, the manufacturer would tell us that there's a voltage that's the most voltage that transistor can handle. If you give it too much, if you give it any voltage below that, the wave that's being traveled along, I want to show this. There we go, that'll do. And that wave is not a problem as long as it's not over the peak of the range that the transistor can handle. But if you make that wave too big, well, what's going to happen? Whatever this line is here, there's the same line for it on the other side of the wave. I might not have this perfectly drawn, but you can grasp the concept. It's outside of the range the transistor can handle it. So what happens is the transistor reproduces all this stuff, no problem, right up until the line. And at the line, oops, let me redo that. I want to erase the line. It can't go anymore. It can't do any more. And we call this the transistor has flat topped. The signal has flattened out. It goes straight across DC. When it does this, the transistor will also, because of it, do some uh, harmonic resonation. It will spit out frequencies you don't want. So not only do you get the signal clip top and bottom, you get distortion. And if the bandwidth of your signal is supposed to be, say, like a single sideband, 3 kilohertz wide, it may be 4 or 5. So not only will a receiver at the or will its receiver at the other end receive missing top and bottoms, but here's the next part. The receiver at the other side, well, it can only see a window so wide. And that signal might be too wide for it. If this is its band, as much as it can see, it's going to be missing part of the signal as well because it's out of its range. It's also going to hear the junk that's being transmitted. You're not doing yourself any favors. I'm going to do a share with you right now. I'm going to share my screen because this is all Jeff's fault. He brought it to my attention. Blame him. I'm just kidding, Jeff. I'm going to take a little minute to talk about a website you really should learn about. It's called www.qrz.com. Now, this is my whole screen being displayed. And this is, I thought, there it is, that website. This website is written by hams controlled and run by hams around the world. The information on this website can be phenomenal. There are databases of all sorts of things related to amateur radio and making contacts and QSOs. There's news about everything from general amateur radio news down to, unfortunately, silent keys, hams who passed away around the world. There are forums for discussing various things in amateur radio. Of course, there's a store for books and things. There's a list of amateur radio swapping shops, so you can find them in your area. And the swapping shops will also include testing sessions in your area. And there are a number of resources here that you can utilize. A lot of amateur radio contests and things that require verification, they do it through this web page. And to be a full member, to get all the privileges, you will have to have an amateur license and put your call in. But you can go ahead and register it as a person who's a student studying to be a ham. And there are answers here for millions of things. Now, Jeff brought up solar activity. There's this little window right here, Jeff. What I didn't tell you is that as a member, this window is a lot more than what it just looks like when you're seeing it. When you click it, there is a whole page, the side of which is all of the current conditions, what band is open for skip right now, what band isn't from various locations, the conditions of the bands, and all sorts of information. Now, I can't find it right now, but if you search around, there's a lady who's, well, I don't want to get you too excited. I don't want to tell you that she's the most glorious supermodel in the world. Actually, she's quite a smart PhD. And she is not that bad of a looker, though. And she gives a very nice presentation on all of what's going on with the sun just about once a week. And she covers what to expect through the week and what's been happening from the week before. Some of it might fly over your heads, and it does fly over mine. Don't feel bad, but after a while, you start to pick up this stuff, and it starts to make sense. And then you know you've got some form of RF brain damage. I don't know why that happens, but it does. There's everything here from ideas on antennas, on there's forums for selling radios, used radios, and there's just all sorts of discussions. You could probably learn everything about anything in amateur radio from the links that this site will take you to if you utilize it. And there's more. I'm not going to go through it all, but I wanted you to be familiar with it. So, in fact, if we looked at general amateur news and we clicked on that, these would be various stories that are covered. There's a happy birthday to something there. Oh, it's the 30th birthday of this website. Isn't that interesting? How to update your FCC license, things like that. So there's a lot of questions that can get answered just by coming to this website. You can also use that website. This website will allow you to search for call signs, either by name, by call sign, by address, by biography, whatever. And if you put in a person's call sign, yep, that's me, I think. Did I eat in there? Yeah, I did. So it must be right. And I search that call sign. Most of the members include a little profile about themselves, and yours truly doesn't because I never got around to it. They give you my pertinent information, my address. The other thing is, all of the people who are signed on to QST can be emailed through QST. You can contact that person. Okay, you can go into QST and um, uh, actually message the individual. I don't do it very often. I guess this is my page, and I've never filled it out, but I guess I should. But in here, it's the details of where my station's located. So if you wanted to work a ham, you hear his call, you can put this call sign in, and it will basically give you the bearings to point your antenna to talk to him. It's here, believe it or not, because it uh, gives my location. Maybe it doesn't give it in bearings. Yeah, I guess they changed that. Look at that. It even tells you how old I am. It says I'm born in 1954, which is true. And then, of course, if they have logged entries and you want to see if you worked him, you want to know if he recorded it, it would be here. I don't use this service for that. You can use as much of it or not. I'm not giving a plug for it. I don't get any benefits from this service. I'm just explaining that it's a wonderful tool, and in it are a lot of answers in amateur radio. Now, to go back to the book. Any questions about that, by the way, now that I flew through it as quick as I did? Okay, which of the following can be used to enter a transceiver's operating frequency? Most modern radios can enter the frequency either by a digital pad, sometimes on the back of the microphone, sometimes on the radio, or what we call a VFO knob. VFO stands for variable frequency oscillator. In the old days, it was a directly controlled oscillator. Today, you're probably more modern radios. You'll be turning a knob which is not directly controlling. It is an encoder sending pulses to a little microcontroller, a little computer inside the radio, and that's what really sets the frequency for you. But the nice thing is it will accurately display it on a digital display. There'd be no doubt about where you've switched to. How much squelch? How is the squelch adjusted so that weak FM signals can be heard? You set a squelch threshold so that the receiver output audio is on all the time. Basically, if you want to hear weak FM, you've got to turn the squelch off. So answer A, set the squelch to the threshold so that the receiver audio is on all the time. Is because if it's very weak, it won't be strong enough if you set the squelch up to any level. It takes and nullifies having squelch on that radio. So it's one of the disadvantages of FM. If FM's strong, you can set squelch up very high and you hear no noise in between the transmissions. But when FM is very weak, you're going to have to listen to noise if you really want to make contact to that station. What is the way to enable quick access to a favorite frequency or channel on your transceivers? Well, first of all, you can mark spots on your dial and have all sorts of whiteout marks all around your radio. I don't recommend that one. But the many modern transceivers have memories. There's different ways in which they're coded or programmed in. Generally, there's some button or sequence of buttons that once you tune a frequency you want to save, you hit the save sequence or the save button, and it stores it in a memory. Most of them number the memory. And so some radios will store way more information than just the frequency. It might store the mode of operation that you use on that frequency, and it might also store, say, a repeater offsets if you have them set, but not all do. Generally speaking, memories save what frequency you're on. So if you want to, you're going to come back to that frequency quite often. You store it in the memory, and I recommend you write down what memory you stored on. Some modern radios will allow you, once you stored a frequency in the memory, to relabel it so that it doesn't display the frequency, but tells you what you've saved that frequency for. For example, if this is a frequency that you always go to for a particular net, you could save that as my favorite net. I don't think all those words will fit in, so you might be initials of my favorite net, and that would pop up on the display screen. If it's a repeater for, say, that you like around town, you know what city it's in or something like that, you might abbreviate and store the city that repeater's in. If it's a repeater, if it's a club station, you might store the club name. You can do those things on some radios, not all. But memories are quite common in most modern radios. What does a scan function on an FN transceiver do? Well, if you depending on the radio, some radios can scan by squelch, some scan just memories, some scan all of the above. Generally, you set the squelch on the radio, and when you set it in scan, it will go through a region, either a memory or just the spectrum that you're in, and you can set it to go up or down. And some of them will automatically go to the end of the amateur band and go back down. Some you have to hit a reverse or a up or down button to change directions. But what it does is it will scan up and down in pretty much evenly spaced integrals or intervals of frequencies. And it will stay squelching until it finds an active signal. Some radios will lock on that frequency once it finds one active and stay there. Others will only lock onto that frequency as long as it's active with a signal, and then will continue scanning when the signal drops off. So whoever's talking stops transmitting, it'll start looking for more frequencies. So the answer here is C. Tunes through a range of frequencies to check for activity. Which of the following controls could be used if the voice pitch of a single sideband signal returning to your CQ call seems too high or low? Now I want to talk about this. When you tune an single sideband signal, when you've got it perfectly tuned, the person's voice should sound just like them. But unfortunately, not everybody is always, especially if you're in a group, not everybody's radio is perfectly aligned with the frequency. They might be off by a hair. And when you're off by a hair in single sideband, it gets either higher or lower. And it's a little bit like Mickey Mousey. He used to refer to single sideband as Mickey Mouse propagation in the early days of single sideband because of this. RIT or clarifier circuits were added. What they are is a frequency shift control on the receiver. When you adjust it, it slightly modifies where the receiver is listening without changing where the transmitter is going to transmit. So you can use that to clarify the audio by tuning the receiver portion of radio just a little off, above or below. So the answer to this question is D. The RIT or clarifier is the device that'll allow you to clean that up, so to speak. Make it a little nicer and more intelligible. By the way, not everybody's voice is really well reproduced on single sideband. The lower your voice or the higher your voice beyond certain points, it's a little hard to get a good reproduction on single sideband. I've been told my voice sounds nothing like me in single sideband, no matter what they do. I don't know why. I mean, I don't think my voice is very low. Anyways, what does DMR code? What does a DMR code plug contain? A DMR code plug is the information for the communications in a DMR radio system, a type of digital radio. It's a carryover from the commercial digital mobile radio code, and it requires what they call plugs, which are basically programmed information. And it allows it to access information that the repeater needs, and it defines what they call talk groups. The full answer down here below helps you to understand this. A DMR transceiver must be set up with all the necessary frequencies, IDs, and codes to be used on the air. They were designed for originally commercial purposes, so they made it kind of awkward because they wanted to be able to have different users that didn't get the same messages and the same transmissions, say for different companies or different users groups. So they established these things called talk groups, and the talk group identification has to be in the code plug. Uh, and so this information is contained in a computer file called the code plug, an old term from the days when special components had to be plugged into the radio. In the early days, you actually had to program up a programmable memory plug that plugged into the, it was an actual electrical EEPROM that once programmed with the information, you plugged it in physically to the radio. Today, software is available to transfer code plug files to a radio digitally. So that's true. You just digitally have to pre-program your talk group and all the necessary information for the repeater you're going to use, and it then will transmit everything necessary when you're operating in DMR mode. Was a disadvantage of having multiple receiver bandwidth choices on a multi-mode transceiver. Well, in order to get you remember I talked to you guys about mixers? We're going to come back to what is the disadvantage of having multiple receive bandwidth choices on transceiver. Remember when I told you guys about a mixer? A
Mm-hmm.
mixer allows you to put two or more uh, frequencies into a mixer, well, usually two at a time. But when you put two in, you get them either added together or the differentials sent back out. And that's how you come up with multi-mode transceivers, is by various stages and various mixers. But doing that, it can permit or create noise and interference of its own. Answer B says permits noise or interference the reduction by the selecting of a bandwidth matching the mode. This is what is the advantage? That is the advantage, that you can strip out the unwanted frequencies. Um, so the B answer explains this further at the bottom there. It says multiple filters allow for you to reduce the noise or interference by selecting the filter just enough bandpass to the desired signal. And that is because we can mix frequencies together, create multiple bands to operate with, and then filter out what we don't need. And we can also, by doing this, we can narrow in the bandwidth that we're receiving with various filters. Today, we do it with digital filters to narrow those things in, but we used to use uh, adjustable crystal filters, and they work very well. How is a specific group of stations selected on a digital voice transceiver? By entering the group's identification code. If you're working on a digital mode that uses talk groups, or they all have different names for them, but basically they're a group of your friends and buddies, all want to be notified and all want to talk to each other, but you don't care if anybody else does. It's not quite for that purpose, but it's sometimes used for that. You got to enter the group code, identification code. Some modes of operation, like DMR, they require a code. Others, like Wires X and Fusion, using the codes are optional. Okay. So if you're going to go talk to a talk group, it's basically because the reason for a talk group is so that uh, when you're talking to a talk group, anyone that doesn't have the talk group frequency uh, ID number set will not be disturbed. Their radio won't squelch and it won't bother them. That's the primary use. And the answer is C. You've got to enter the group's ID code. Which of the following transceiver bandwidths provides the best signal to noise ratio for a single sideband reception? What they're referring to is if we narrow the bandwidth that we're receiving, you know that a single sideband signal is roughly 3 kilohertz wide, which is 3,000 hertz. And if you had a 2400 hertz filter, it would narrow it down, narrow in, but you wouldn't lose a lot, okay? But you would lose the very edges of the signal. But that can help you by eliminating noise close to the frequency. In Morse code, you could narrow much finer. You could go down to 160 or 180, maybe 200 hertz filters, but you can't in sideband. And if you were narrowing in an AM signal, you'd probably want it somewhere around 500 hertz because of or 5,000 hertz because a AM signal is about 6K wide. You only can shape a little off each edge or it starts getting distorted. But it will help clean things up if you do that, narrowing the signal. And that's done by either digital filtering or, again, variable filters that are crystal controlled. Which of the following must be programmed into a D-star digital transceiver? It's another mode of digital operation, D-star, before transmitting. Well, D-star and Fusion require that you enter your call sign. C4FM is the same as Fusion. It's a Yaesu system. I think D-Star is a Kenwood system, but I might be wrong. But they both require that you enter your call sign into the transceiver and that it sends that as part of your digitally, electronically, as part of your signal. Now, important note here, even though digital radios send your ID, your call sign when you transmit, many do, some don't. Even if they do, you still have to ID on the air just like you would in any other radio. You have to ID every 10 minutes and at the end of the QSO. And that is because even though it's digitally provided on every time you key the mic, that is because the law says that you must ID either in the mode you're operating in, which is your voice. Even though it's digital, the digital information being sent is not your voice. It's not being sent as a voice, it's being sent as digital data along with the signal or Morse code. And that's not either of those. So you must identify. Okay, what is the result of tuning an FM receiver above or below a signal's frequency? Well, uh, in FM, they're referring to here, if you tune just a little above or a little above below the frequency, you'll only get a portion of it in your receiving bandwidth. It will be distorted. Just like in single sideband, it'll be distorted, but it will be a different type of distortion. You'll once you start playing with radios, you'll be familiar with that. So if you're not quite on frequency, you will hear a distortion. T5, it covers voltages, ohm meters, watt or ohms, watts, insulate, all sorts of fun stuff. This is basic electrical. Electrical current is measured in which of the following units? Well, we measured current in amperes. I covered that when I covered the E equals IR formula. Voltage, which is electromotive force, is equal to the current, which has the symbol I, times the resistance in ohms. Current is measured in amperes. When electrical power measurement is used or is measured in which of the following units? Power is measured in watts. Power formula is P equals IE or pi. And we covered that. What is the name for the flow of electrons in an electrical circuit? The flow of electrons, the movement of electrons is defined as current. The answer is D. What units, what are the units of electrical resistance? Well, the answer there is resistance is measured in ohms, OHMs. By the way, conductance is measured in mhos, MHOs. Doesn't that seem kind of odd? Conductance is the opposite of resistance. A wire has a certain amount of resistance, but it's also a conductor that provides current flow through it. So it has a level of conductance. It's the opposite of resistance. Seldom in radio electronics do you need to know that, but in some physics of electronics, it's important. What is the electrical term for the force that causes electron flow? Ah, well, what is it? Well, I'm going to make this simple. We have two formulas, E equals IR, the ear formula, and the pi formula, P equals EI. And the E is electromotive force. So what is the term for the force that causes electrons to flow? Well, the force or the push, the unit of measure is voltage. And the answer there, of course, is voltage. It's represented in an equation that says below as E, electromotive force or electric potential. Um, what is the unit of frequency? It used to be cycles per second because that's how many times a second a wave passed through zero and back again. But at some point in time, they decided to honor the great electrical researcher and physicist Hertz. That was his name, I think Johann Hertz, but I'm not positive. I think that's right. And so today the measurement is in hertz. Why are metals generally good conductors of electricity? Well, the answer here is they have many free electrons. Actually, they have many free electrons in the outer shell, but many free electrons is good enough. And it's the whole idea. That's why a conductor can conduct. It has electrons that are free to move. So conductors like copper and gold are the best of conductors. Silver is a good conductor. Aluminum's a pretty good conductor, but all metals are conductors. Some better, some worse. Which of the following is a good electrical insulator? Well, insulators are materials without free electrons. Of the list there, all the others but glass are conductors. Glass is a great insulator. So is dry wood, paper, a lot of plastics, not all, and all anything. Well, not anything, but most things that are non uh, metal. Which of the following describes alternating current? And an alternating current is a current that goes from positive to negative to positive to negative to positive, negative, back and forth. And the fact that we represent a sine wave is because it ramps up and ramps down. It slowly goes up and goes down. There are pulsating AC signals that first switch high and have a constant voltage, then switch low and have a negative voltage, then switch back high, have a positive voltage. We call that square wave AC, but the truth is it's just on and off of a signal that goes between positive and negatives. It's not used so much directly in radio electronics, but it does exist. That's a current that alternates between positive and negative directions. So the answer is C. Which term describes the rate at which an electrical energy is used? The rate at which you use energy is power. Power is the consumption of energy. It is referred to in physics as work. Power is that you've done something with the energy. And the measurement, of course, is in watts, and the measurement and power is symboled with the letter P. What type of current is opposed to by resistance? And the question here is answered with A, direct current, B, alternating current, C, RF current. And the answer is D. All currents are opposed by resistance. Not all currents are opposed by inductance or capacitance. There, uh, uh, inductance and capacitance have little effect on DC circuits, but dramatic effects on AC circuits depending on the frequency. What describes the number of times per second that an alternating current makes a complete cycle? Every time, the number of times per second that a current goes positive through zero, through negative max, goes back up to positive again. When it goes from zero up to positive max, back down to zero, back down to go down below to negative max, back up to positive. One complete sine wave, that is the frequency. And so the unit that describes the number of times per cycle that an alternating current completes a number of times a second, it completes a cycle, is frequency. That's why it used to be measured in cycles per second. Hertz describes cycles per second. By the way, if you've got a 50 megahertz cycle, that's 50 million times a second that the frequency goes from zero to positive max, back down through zero to negative max and back again. That's 50,000 waves, or uh, uh, yeah, complete cycles, 50,000 cycles of the wave. Okay. Frequency is always displayed in a fancy lowercase f, uh, and it's usually drawn with a curve at the top and the bottom with a cross letter. But your typewriter keyboard can't do that all the time, so we just use a small f. And there's an illustration in the book, and it's going to be the last thing I'm going to go through today. And it shows this. This is a wave. This is one cycle. That's half the wave right here, and then there's the other half. Then the wave again is another cycle. If this interval is 1 second, that's one cycle per second. If it's 2 cycles per second, it will be double. If it's 3 cycles per second, it will be triplet. And by coincidence, this is the definition of harmonic. There are relationships between frequencies. In music, harmony sounds really cool because these signals have intervals where they process through zero, and a shared basis and harmony of the right frequencies, usually 1357 creates a chord and it blends together beautifully. So the first fundamental frequency, that's one. The third harmonic, that's three. Five, the fifth harmonic, and the seventh harmonic make a seven uh, uh, harmonic chord, like an F7 harmonic. Okay, I'm not a musician. Musicians could better answer that. I have some familiarity. I can almost play some instruments. And so I want you in your book, you're going to find this particular chart. I want you to pay attention to it. If I haven't mentioned it before, I'm going to close on this tonight. This chart won't give it to me. Okay. This chart tells you what the metric prefixes are. Whatever base unit is in metrics, and we use them for everything from volts to amps to ohms, everything. Million volts is a megavolt. A billion volts is a gigavolt. A teravolt is whatever 1,000 times a billion is. Is that a trillion? I don't know. A kilovolt is 1,000 volts. Same thing with watts. Same thing with anything. But we measure, um, but capacitors are really small values to be very effective. You'll find that we use milli Henry. Wait a minute. Millifarad, microfarad, nanofarad, and picofarads for capacitors a lot. But you also found that we use like values for resistors of oh 50 ohms, 5,000 ohms, which is 5K. We use a mega ohm, so on. But we also use milliohms and micro ohms and microvolts, millivolts, even nanovolts for some things in electronics, even as small as picovolts. So all these units of measures are important. They're multiples of 10, starting with the base unit, which really should be right in between desa and deca. They should have a line there. Draw one for yourself on your own chart and learn them. Get used to them. You're going to use them a lot because when you look at something that says you need a 20 picofarad capacitor, you don't want to put a 20 milli or a microfarad capacitor in there. By the way, capacitors, picofarad used to be written up as microfarad. It'd be double the Greek letter U or Greek letter mu. It looks like a U with a long tail. It's really the Greek letter M, small case. The rest of them are in pretty much standard English letters, but they throw in the physicists threw in all sorts of other stuff.